label in that the section over here, so anything that is in this section, makes it a solid. Anything in this little middle section makes it a liquid. And then this section over here is when it's a gas. Okay, so for example, for carbon dioxide, if I'm at a temperature of 197 and a pressure of 5.2, it would exist as a solid. Right on the lines are when the phase changes happen. So if I have something that changes from here to here, what's it called when something goes from a solid to a liquid? Melting. So that would be the melting of it. And then the reverse would be?
Condensation.
Oh, that's another one.
Freezing.
There you go, freezing. So when you cross those lines, that's where we get our phase changes. So what do you think it means when something falls right on the line? What phase am I in?
Transition phase.
Yeah, like both, right? So if it's right here, it's both a solid and a gas at the same time, right? Okay, so what does it mean? What's it called when something goes from a liquid to a gas? What's that phase change? Evaporation or boiling. And then the reverse of boiling is? That was when Jay said that's our condensing.
So is there a lot more options to get a solid or a gas than there is a liquid?
Like in terms of,
Like
yeah. So at least for carbon dioxide, it doesn't exist as a liquid except under very special conditions, right? And then this is the phase change that maybe isn't as common. Does anyone know what it's called when something goes straight from a solid to a gas?
Oh, I know.
Sublimation.
There you go, good, sublimation. So that's kind of a cool process. A simple example that you've probably all seen is dry ice. Because if you have a cube of dry ice, you won't ever see it melt, but the cube will get smaller and smaller and smaller.
What's the opposite? I think it's smoky.
What? It's just carbon
I know
dioxide.
you don't.
Oh yeah, can you like suck it in? Yeah, there's lots of fun things in your dry ice. Anyone know the opposite of sublimation? There you go. Yeah, so the opposite is deposition.
What?
Okay.
Deposition.
So that means something goes straight from a gas to a solid. Okay, so with this, this kind of goes along with the process of making dry ice, is the higher the pressure, right? When pressure is really, really high, you see it favors it being a solid, right? Because that makes sense because we're pushing them really, really close together, okay? So here's just some other words meaning the same thing, right? Melting we could also call fusion. Freezing you could also call crystallization or solidifying. Boiling you can also call evaporation or vaporization. And then there's condensing. And then the ones that are a little bit newer possibly is sublimation. That's when we go straight from a solid to a gas. Obviously, in order for this to happen, you have to have an input of energy. Another place this happens actually is at very, very high altitudes. The snow on top of the mountains will disappear, but it's never actually melting because it will sublime in that process. So, and then deposition is when we form a gas to a solid without it ever liquefying. And this is going to release energy in the process. Yeah. Okay, so when we say normal, remember we're talking about standard temperature and pressure. That's like sea level. Okay, so unless they tell you otherwise, assume we're at sea level. Okay? Yeah, normal means standard. Okay? So if the question says, hey, under normal conditions, assume it's standard. Okay? So once again, in the way we read these graphs, it's a balance of connecting the 2 points. There's a really cool point on the graph known as the triple point, which is where all 3 phases actually exist at the same time. So maybe draw a line from that definition to your graph to remind you what it is. That right there is the triple point. And if I can be at exactly 216 degrees and 5.2 ATMs, you can get solid, liquid, and gas. It's boiling and freezing all at the same time.
That'd be cool.
I know.
What does it do? Just
Can we actually do that?
So let's say, for example, in reading this graph, if I'm at 200 Kelvin and 2 ATM, for a smiley face, grab your periodic table and tell me, would this substance be a solid, a liquid, or a gas?
Which one?
So we're doing the first one. So if I'm at 200 Kelvin, so find 200 Kelvin on your x-axis. And I know the scale's kind of weird. Okay, and then find 2 ATM on the y-axis. Connect the 2 points, and then show me which section it would fall under.
is it A, B, C?
Yeah, so we'll do solid A, liquid B, gas C. So what phase would it be under those conditions? And I'll give you the benefit of the doubt if you just read the graph wrong, because the scales are a little bizarre.
Solutions, gas?
All right, so
What's A again? Yeah.
that's where 200 is about,
Where?
and that's where 2 ATM is.
Yeah.
So it should be a solid. If you just read this scale weird so it shifted you into the gas, your logic is right. I just know the scales are a little wrong. But does that make sense how you read it?
Yeah.
Okay, all right, let's do another one since that one tricked some of you. So for a smiley face, tell me this. Ready? So I'm here, okay? If I increased my temperature to 300 Kelvin, same pressure, what state would I be in now?
Oh, I got that.
Same pressure, but 300 Kelvin.
B.
Good, yeah, that means I'm still here because I'm still at 2. 300, I'm traveling this way, so what process did it just go through? Sublimation, yeah. So through this graph, you can find phase changes, you can find what phase it's in, predict how it will change as you change different conditions. So, good, have a smiley face for that one. Okay, another key point on your graph is known as the critical point. Okay, so draw it after writing the definition, and then draw a line over to this point on your graph. This right here is the critical point. What the critical point is it's at this temperature, it doesn't matter the pressure anymore. It's always going to be a gas. Basically, it's just once you add enough energy, there's no way to condense it down. So in a sense, at that point, the graph goes straight up. So a lot of times the graphs will end, but at that critical point, you can imagine that this dot, it just goes straight up for eternity. Because once I hit this temperature,
You can't get it any hotter.
I can get it hotter, but it's just saying that no matter how much pressure I apply, right? If I pressure, it doesn't matter. It's going to still be a gas once I get to there. Crazy pressures and temperatures up there, but yeah. Holly.
Is this graph, like, does it work for all the elements?
This one in particular is structured for carbon dioxide, but any phase diagram you look at would have a similar type of shape. Yeah, so we'll look at one for like an unknown on your assignment today. Okay, so evaporation is kind of an interesting thing if you've never really thought about it, right? So when something evaporates, what's the phase change it's going through? I'm going from a liquid to a gas. But when something evaporates, it's happening below the boiling point. Right? I don't know if you've ever thought of this before, but a puddle doesn't boil outside, but yet the water disappears, right? Which is kind of interesting because it's a good thing it didn't boil, because you could imagine how dangerous puddle jumping would become.
That'd be
Right?
sick. Or no, but then like you'd have like a lake just boiling.
That's the thing, yeah, our lakes would be like boiling, right? So the way that it works is, imagine this, everyone. So the molecules on the surface steal energy from the molecules underneath so they can evaporate. So what would that say? If they're taking away energy from the ones underneath, what's happening to the temperature to the ones under it?
Getting colder, so that's why the cold finally down the colder it gets.
So that's part of it, yeah, so that as they steal this energy away, the substance that is left behind is actually lower in temperature. Right? So another example of this that I'm sure you've all experienced is, so you take a shower, and then when you get out of the shower, you get cold. Because the water is evaporating off of your skin, and to evaporate, it's stealing the heat from your body. And so it makes you cold, right? Same thing happens, like I call it my after run chills. After you exercise and you're really, really sweaty, even if it's like kind of hot outside, you can often start feeling cold. And it's because your sweat is evaporating off your skin, and as it evaporates, it's stealing your heat. Right?
That'd be crazy. Like if it was to boil to evaporate, you'd burn light every time you got wet.
Yeah. Yeah, so that's why it's a good thing that doesn't, or it just would never happen because it wouldn't have enough energy, right?
Yeah.
So, and then the same thing happens with condensation, because condensation is happening below the boiling point. So what's happening here is that the molecules are slowing down and sticking together due to those intermolecular forces, and since it's the reverse, it's actually a heating process. So when water condenses, it actually makes it a little bit warmer.